Let's start. For those of you that missed the first class, I'm Avi Mendelson. For those of you who was in the first class, I'm still Avi Mendelson. And the name of the course is Deep Learning on Hardware Accelerators. So finally we reach the hardware side. Again, it will not be a course on hardware, but I'll try to cover at least those aspects which are important of the hardware, which are important in order to understand how to run the deep learning algorithms in efficient way on GPU, for example. Maybe we'll discuss other architectures as well. So what we'll do today? First of all, we start with some basic concept that we need to understand, or at least to touch bases for those of you that studied computer architecture a long time ago. But again, we will focus only or mainly on the features which are interested to our class. I will mention some other things, but we will not go into any details about all the other algorithms. Then we'll go to, I think that this is a very interesting session, how deep learning algorithms are actually implemented on GPUs, and we'll see that it looks very, very different. It's not just a matter that we execute the same program in a different way, but we need to think differently about the algorithm when we deal with running it on accelerators. After understanding it, we'll move to a little bit about the GPUs and the Nvidia architecture, and then we'll connect it to the programming model, and we'll wrap up at the end. Again, if you have questions, please ask, and if I cover things too fast, tell me. If I'm too slow, again, and if you want me to extend any of the topics, please ask questions. So, we'll start with a very, very basic. I think that I showed this slide in my first class. What is von Neumann architecture in general? And this is amazingly simple. What's really amazing about this architecture that if we fully understand the von Neumann, we'll see that most of the architecture today are still implementing von Neumann architecture, although it was invented something like 60 years ago. So the main idea is the instruction and data are in memory. It can be, later on we'll see that we can break the memory into a hierarchy, but the program it is executed in the code order, or what we call control base. So we take instruction by instruction, instruction by instruction, and how it is executed. We made a fetch. Where we fetch from? From? Yeah, but the memory is big. No? How? You put a system. There's nothing in the instruction cache. There's nothing in all the internal structures. What did the computer do? There's a register which is called either program counter or sometimes it's called instruction pointer. And when the system reach the fetch, it just go to the address which is written in this address and fetch the instruction from that point. Later on, what does it mean that we have a jump or we call something? We just change the address in this register. So whenever we fetch the instruction, the machine assumes that the next instruction is, where is the next instruction? What? Usually it is not 1 byte for sure. If it is RISC machine, it is 4 bytes. If it is x86, it is somewhere. Because you need to understand what is the length of the instruction, and then you know that the next instruction is just after it. But we assume that we have instruction by instruction, instruction by instruction. So when we fetch something, there is some side effect that automatically this register go to the next instruction. So next time that we reach the fetch, if nothing happened, if we didn't change the address, so we will fetch it from the next instruction. This is why we are actually going instruction by instruction. So we fetch and then we decode what we decode. Now after we fetch, we have it in the instruction buffer. So now we can decode it. So it tells us what we should do and we execute. Amazingly, the execute is something which is not that trivial, because if we just look in the Neumann architecture on the memory, the same location, for example, we want to add two numbers. The same location, if it is in a memory, not in the register, can be interpreted as integer, as floating point, as a character, as you name it. And the only difference is that by knowing what is the instruction, so there is a different instruction for add integer, and then the machine assume that we add integers, and add floating, and then the machine assumes that you are adding floating point. So we have the memory right back, and we are going back to the fetch. So this is the only thing that the machine is doing. It doesn't matter if you have 8088, which was about 25, 30 years ago, or you have the recent Skylake or the next architecture. This is in general what the machine does. The only difference is that we try to achieve more performance or better power. But the basic architecture is all the machines in the world are doing the basic, not all, most of the machines in the world, this is the basic thing that the machines are doing. So, if we assume that every step here takes 1 clock, so actually we finish this cycle every 5 cycles. It means that our IPC is instruction per cycle, is 1/5. Why it is 1/5? Because we have 1, 2, 3, 4, 5, 6. So it takes us 5 cycles before we reach the next one, which is quite bad. By the way, what does it mean if we run at 1 gig frequency? You have on the processor 1 gig. So if the IPC is 1, it means that you are executing 1 billion instructions per second. This is the meaning. So many times people tell me, no, this is something very rare. It happens only once every millions of times. Yeah, once every millions is less than a second. We now just need to understand the relation here. So, in this case, we have a frequency of 1/5. And if we assume that 20% of the instructions are load and store, and the access time to the memory is 100 cycles, so what will be the new IPC? It is not very trivial. I'll do it very fast. I don't like to spend too much time, but in general, what we are saying is that we have 1.8 of the instruction we didn't change it. So the IPC that we say was 0.2. You understand why? Yeah. Plus, in the 20% of the time, it will be 1/100, approximately. which means that if you make all the calculation, it drop your performance dramatically. It drop, even if you have this ratio, it drop your performance dramatically, and this is the reason that we care so much about the memory latencies, or what we call the memory wall. Because even if, and by the way, in the modern world, the accessing to the main memory, usually it's few hundred cycles. In the case of Nvidia, it can reach up to 1,000 cycles to reach the main memory. This is because some design consideration that we'll speak later on. So memory wall is one of the most important part in order to get performance out of a von Neumann machine. Yeah. No, the memory of the GPU. Yeah. We'll address it later on when we talk about the Nvidia architecture, but in general, Nvidia builds an architecture that they are much less sensitive to latency. Now, since they want to save power, which is very important for them, or in general, so they prefer to do things with a slower frequency and spending less power, and to get a high bandwidth. So they trade a very wide accesses with a lot of memory ports to the memory, but do it in a slower pace. So this is their trade-off. So is there any other alternative to the von Neumann? Apparently, yes. Oh, sorry. This is the problem that I cannot see the next slide. Okay. So what we can do in order to achieve more performance. So we can actually do pipeline. I will not go into all the details, but the idea of the pipeline, that now, instead of waiting 5 cycles, so every cycle something is finishing. And since every cycle something finishing, so actually the throughput of the system is 1 instruction per cycle. You ignore the filling up the pipeline, but in general, and if we put more pipeline stage, we can even accelerate the clock rate. In Intel, many times ago, there was architecture that was called a P4 or Nehalem. No, what was the name? Tejas was one of the version that they work on. And at that architecture, actually, they had something like 50 pipeline stages. Why? Because they wanted to reach very, very, very fast a clock rate. It costs a lot of power. This is the reason that they stopped doing it. But in general, we can expedite the clock rate. And of course, if you expedite the clock rate and you finish every cycle, so you're getting more instruction per cycle. And this is the purpose. But it is not sufficient. Because the instruction per cycle, notice instruction per cycle are not sensitive to the frequency at all, because it is per cycle. Cannot exceed in this example on this architecture 1. And now, when we have long pipeline or even short pipeline, now you need to solve the problem of branch prediction. Why? Because we fetch something. When we fetch the next instruction, next cycle. But we don't know if this instruction was a jump or not. So we have no idea if we should take the next instruction or wait until we know about it. So we cannot wait. If we want to do something fast, we cannot wait. So we put a lot of prediction, we put a lot of mechanisms that actually try to predict what will be the behavior of the system. By the way, branch prediction is one of the first places that people implement machine learning. It's called perceptron branch prediction. This is one of the revolutions that people made a few years ago, and they actually use it inside the architecture. So all the idea here is to predict when we need to jump. But this is not the only mechanism. We need to solve the memory wall. So in order to solve the memory wall, we put a cache hierarchy. What is the idea about cache hierarchy? That usually we use the term of the 90-10 rule that says that 90% of the time we are accessing 10% of the code. So if we just put this 10% in a very fast memory, so on average we're achieving very good access time to memory. We will not go on all these details, but we'll see that in GPUs it will be very, very, very important, although we will not use a cache as it is in the CPU. We will use some other structure, but the same idea that they try to have some hierarchy of memories, that you have a very fast access to something which is very close to the CPU. And we use a lot of prefetching. Prefetching is try to bring something ahead of time. So, for example, we execute instruction by instruction. So even if we execute one instruction, we may assume that we will execute the next instruction sometime. So when we access this instruction or this cache line, we automatically can go and bring the next cache line. And this is a very, very simple mechanism of prefetching, but we can also have software prefetching, that we ask the software actually, or the user, to tell us what is going to execute next, and then the compilers try to take care about it, the architecture take care about it, etc. And the third parameter that we have today is the power wall, because sorry, in most of the system, power is the one of the main effect that limit our performance. So people say, okay, what is the connection between power and performance? So apparently, power controls almost everything today. So if we are using handheld devices, it means that we are running out of battery. But if we are a server and we don't have any problem of battery life, the temperature of the die cannot exceed some thermal point. Which means that if it exceeds this thermal point, what's happened? What? In the worst case, it will come back to sand. So if you don't know, silicon is sand that will go to some process, and you can make it back to be sand. As somebody says, that it is very, very expensive sand. So there are mechanisms that try to prevent it, which means that whenever you start to reach the temperature, which is dangerous, the system don't allow you actually to do it, and then it starts automatically to reduce the frequency. What does it mean to reduce the frequency? It means that you are slowing down your system, that you are losing performance. So if you try to do something very, very, very sophisticated, at the end of the day, this mechanism slow you down. So you cannot exceed some limit of performance because the system doesn't allow you to go beyond some thermal point. By the way, there is a big argument what is better to have the GPU. We'll talk about programming GPUs, to have internal GPUs or external GPUs. And what is the main difference between external and internal? The cooling. The cooling, because if you have internal GPU, actually the same cooling need to cool the CPU and the GPU. And if you have external, so you have one cooling device for the GPU and one cooling device for the CPU, and then you can have much better cooling system. Okay. So I asked if there are other alternatives, and apparently there is another alternative, which is not very common, or at least not in that a sense is very common, but it starts to be more and more common, and we'll address it. It's called Dataflow Execution. Dataflow Execution says you don't need to execute the instruction by instruction, because what you really care is about the correctness of the result. The correctness determined by the data dependencies. Data dependency says that whenever you have two inputs which are ready and you have something to write the buffer to, so you can execute the instruction. So if we just take this sequence of instructions, so in order we need to execute the first instruction that we assume here that it takes 3 cycles, and we cannot do anything during the time, and only then we can execute the rest if we have enough resources. So here it assumes infinite resources. But in out of order or in data flow, so we can execute 3, 4, and 5, which means 1, 3, and 4. We can execute before, so we can execute 1, 3, and 4 in parallel. When we finish 3 and 4, we can execute 5, even though instruction 1 have not finished. So we can actually execute the program in much more efficient way. More than that, we can show that if you build the system correctly, so you can achieve the optimal execution time in that sense. So Dataflow execution is much better than in order. And more than that, you can, in this case, you can achieve IPC greater than 1, what we couldn't achieve before. A small question is why we are not using it. By the way, people try to build this system. What? Not exactly. I'll address it in a minute. Not in that way. But in the past, in Manchester, there were Dataflow machines, Manchester 1, Manchester 2, Manchester 3. In MIT, they built the Dataflow machines. All of them didn't come commercially success. And the reason is not the hardware. The main problem is that it is terribly hard to debug such a system. Because if you have a problem, you have no idea what's happened. You have no visibility. You have no idea if the problem is a hardware, software, algorithm, what's happened. So mainly because of this reason and few other reasons, because of internal bottlenecks, the pure Dataflow machine never succeed. Not really true, because we will talk about FPGAs in one of the future classes. The FPGAs can implement Dataflow machines. But more than that, if you look on what we call out-of-order execution, so out-of-order is a brilliant idea that from the user perspective, we have in-order machine. So instructions are coming in order, they're leaving the system in order. So for debugging, for any purpose, this is in-order machine, but internally you can execute it out of order. And this part of the out-of-order execution, this is what we call limited Dataflow machine. By the way, more than that, externally, we have a CISC architecture, which means that instruction has different instruction lengths, etc., etc. Inside, we have RISC machine, because RISC machine is more efficient. So even though Intel very proud to say how we have CISC architecture, when they really need the performance and the power, they use CISC architecture. The risk architecture inside. So we will not go into detail because it is not the main purpose of the course. It will not contribute to our course, but I just wanted to mention it. But the bottom line here is that all these mechanisms are nice, but they consume a lot of area and power. And this is the reason that all these Intel architectures start to be very, very inefficient in terms of power in compared to simple architectures. And the question is, can we do something in between? Can we achieve something that will give us the parallelism, but will not consume that much power? And this is the main goal of the new architectures. Yeah.
In this scheme, the front end is shared between several processes, and the parallel execution is parallelizing only the execution of those processes?
The answer is yes, but we are not going into details. In the front, you just mark like with colors. You say these are the blue, green, red, etc. So each time that you fetch something, you mark it, and when you go to the commit, so actually you distribute them to the right places. So it can be MOOCs, it can be few instruction here, few instruction there, but yes, in general, you may assume that you have a music park and you have a queue of buses that come. So in the buses, everybody it's in order, and then everybody go to whatever they like. But when the departure back, so everybody go back to the bus that he arrived, and tell his friends what he saw in the amusement park. So it's in order. They go back home in order, but inside everybody can do whatever he or she likes. So this is the basic idea here. So the question is, can we do something in parallel? Because we see that if we are not doing something in parallel, so we are limited to IPC equal 1. So can we actually do things in parallel but without paying all the penalty? So there are different attempts. Some of them are what we call automatic parallelism, that we are writing sequential code and the hardware compiler translates it automatically. If you like the out of order, do it that way. It takes the sequential code. You find dependencies. We will not go into detail how, but you find the dependency and then it execute it in parallel. Or we can ask the user to tell us what is the process, what is the thread, what is the difference between processes and threads. Yeah, threads share the same address space, processes has different, but by the way, today in the new operating system, there is no difference between process and threads. This is an implementation issue. So, and we can go to what we call user-defined fine-grained parallelism. For example, there are vector instructions like AVX. What is vector instruction? Vector instruction is that the user tell the system all these instructions are not dependent on each other. You can execute them in parallel. You need to decode it once because I'm going to use the same instruction and I'm going to send it to all the execution units. So this is what we call single instruction multiple data. And the user actually tell usually what is the length, how many elements, what all the instruction will do, and there is special hardware to implement such vector instructions. And there are approaches to do somehow the software interface like in CUDA. We'll address it later on. So just an example of a vector instruction. So in the sequential call, we might say for integer I to n, do AI equal BI plus CI, we can see that each of the instructions is independent on the other. The compiler may see it by itself, or the user may do the analysis, and it says, okay, instead of doing it in loop, I will tell you, take 5 instructions and do it in parallel. It is okay. So there are languages like OpenMP that we can say for all or do all, and then the system understands that this is parallel, or we can write it in vector operations. And in Intel, for example, you have different instruction for each length. So you wonder how many instructions we need in order to support it. And the answer is a lot. In Intel today, before the AVX 512, they had 1,500 instructions. But I think that with the AVX 512, they add more than 100 more instructions just to support it. And this is the reason why they can do it, because they have variable size. So they try that the instruction which are most commonly used will be short instruction and the rest will be longer. So they believe that the compromising is correct, and there are other reasons like UOP cache, etc. But forget about the hardware. The software, each time that if I want to take advantage of AVX 512, most likely I need to recompile my code. Sometimes I even change the algorithm, but each time that I change, I take a new architecture, either I use the back compatibility and then I'm not gaining the new features, or I need to compile my code, I need to test it, I need to verify that it is correct, by the way, usually it is not, and I need to deal with the efficiency, etc. So it starts to be very, very difficult to deal with these instructions, and there are very few people that actually know how to program this instruction properly. Yeah.
Modern compilers, like if you download, I don't know, Visual Studio, does they automatically adapt if the system has support for AVX, or should I program?
Usually there is a switch in the compiler that you need to tell the compiler that I'm using this and this AVX. There is a technology that calls binary translation, that the system can do some of these things automatically. The way is that when there is some agreement among all the CPU manufacturers, there is some standard to what they call a CPU ID. CPU ID is a format that tells you exactly what you have in the system, which means what technology it supports and what is the organization of the cache, and etc., etc. So very sophisticated algorithm. The first thing that they are doing, they just look at the CPU ID, and then they say, okay, if you have AVX 512, so I will use this version, etc. This is very nice for academic work. In practice, usually if you want to release something, you need to do a software quality assurance, and then for each one of the architecture you need to have a different quality assurance, which means that usually you will have a different binary for each one of the technology, and it starts to be a mess, and most of the companies do not do it unless this is something which is highly demanded or highly used. For example, for machine learning. So people are doing it because they want to get the best performance. So the other thing which is important is, in order to get parallelism, is just to run multi-threaded. And this is very important both for the GPUs. This is the reason that are extended a little bit because there are different types of multi-threading. The idea is that the same hardware is used in order to support multi-threading. From the user point of view, it is at the same time. What does it mean? If I just use one thread, so we see that sometimes I'm using all the resources, sometimes I have slot that I'm not, the system is stalled, nothing happens. By the way, if I access the main memory, it can be hundreds of cycles that the CPU doesn't do anything. So the question is, can I full it up? And one of the option is what we call fine grain. The first atom of Intel did it. So I have 4 threads, so I'll do 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, round robin among them. What does it mean? It means that actually when I access the memory, I have 4 cycles in order to get the information in. If I'm not getting the information, so I'll wait for the next cycle. So there is no sophistication, but it is very easy to implement. The other is what we call switch on event, and this is very, very important because this is what is used by the GPUs. In switch on event, you execute something until you reach some condition. The condition can be some timeout that expired, or it can be some long latency instruction, or sometimes, if it is very efficient, it can be even branch. I reach a branch, I have no idea if this branch is taken or not taken, so in parallel, I continue to execute in order to get the result, but meanwhile, I switch to another thread, and another thread continue to do the work. So I do one, I move to the second one, to the third one, to the fourth one, and then I go back to the first one. Hopefully, the condition that actually stopped me here is over. For example, I'm waiting something from the main memory. Hopefully, here I execute enough instructions so when I return to the blue one, the information is already there.
One pipeline, so even if you switch the thread, how you implement it in the hardware, one thread keeps working, and you make another thread, the main thread.
For example, let's take the simple example, you wait for the memory. What's happened is when you wait for memory, usually the logic that brings the data from the memory to the CPU has nothing to do with the CPU.
Of course, but the pipeline is still loaded with all your previous prefetches and all your previous...
Okay, so you're right. So some of the mechanism here flush the pipe, like in branch prediction, do the same as branch prediction. There are techniques that you just freeze the pipeline. The Professor Shachar Kadinsky did a nice work and show how to do it. But usually you just flush the pipe, assuming that here it's not for exam instruction, but here you execute few hundred instructions before you stop or switch, so the penalty is relatively low. But we will address it when we reach the GPUs, because in the GPU this is exactly what they are doing. We can partition the resources statically. I'm not going to it. We can do what is done in very sophisticated processor in Intel, in IBM, what we call simultaneous multi-threading. Then we said that we fetch in order and we execute out of order, so the out of order can take instruction for any thread in the system. So we fetch it in order. Usually we just decode few instructions for one thread and few instructions for the other. We have enough instruction in the pool, but when they are in the pool, we mark them, but the execution unit don't distinguish where they came from. So each time that something is free, so it just execute it, and then we just mix everything, and we pray that we will not have a live lock, deadlocks, etc. in the system, and praying is a very efficient way here. No, actually, there is a lot of work in order to validate and our mechanism to make sure that nothing bad happens. So we'll go to this aspect when we'll discuss the GPU. So this was a very, very fast introduction to hardware. Again, if you have questions, something approach me later on. But questions? Okay. So now I want to move to something that at that point it will not be directly connected to what we said before, but I want to speak a little bit about different ways to implement operations of deep learning. So first of all, when we write something, usually we write it as nested loops. For example, we want to do convolution, so we have some window, and we told yes, we take the window and we shift the window with the stride, etc., etc., etc. This is the way that we describe it when we are talking about sequential execution. Now, when we go back later on to GPUs can be very efficient only if they have massive, massive parallelism, which means millions of operations that can be done at any moment in parallel. If you just look on this algorithm and say, okay, so I have nested loop and it can be 3 levels, 4 levels of nested loop, it is very, very difficult actually to extract the parallelism out of the structure. So the reason that, one of the reasons that working on machine learning start to be very practical was when they found out that we can actually convert this sequential approach to something which is extraordinary parallelism. Simple example. We have this convolutional network. So when we have this convolutional network, what we are saying, we say, okay, we have this network and we are connecting all the points to all the points, and we calculate the weighted sum of this point. So we try to do the sigma of all the inputs here. I can try. On the other hand, so if we just write and I have the code later on, we'll see that what we have is a nested loop of go over all the inputs and calculate the weighted sum, etc. This is tremendously a sequential process. On the other hand, we can represent the same problem by having the matrix multiplication. So if we just stack this matrix multiplication, so all the connections here, or if I look on this point, so all the connections here are this column, and I multiply it by some feature map, and what I'm getting is one point, and this point is exactly the output that I will get here. So just by doing this multiplication, what I'm getting is that it automatically compute all the outputs by doing a regular matrix multiplication. For each one of these cell will be the output of this passepartout, the neural here. Now, if here I will take n filters or n channels, so I can get actually the output will be the output of fully connected with n channel with n features. So what's happened is that we took something that looks tremendously sequential because of all these nested loops. And when I'm doing it in matrix multiplication, in matrix multiplication, we have a lot of method that we know how to do matrix multiplication in parallel. So we just take this representation of the problem, we feed it into some of these libraries that knows how to parallelize matrix multiplication or all this linear algebra, and immediately we are getting all the parallelism in the system that we need. More than that, there is a lot of knowledge how to break it into chunks which are of the size of the cache, for example. So because linear algebra was used for many, many years for many, many purposes, and people optimize it to death to all the different architectures. So now if we can represent the fully connected layer as an operation between matrices, so we can leverage all this parallelism. And this is exactly what we are doing in CUDA or in GPUs. The difficulty here is that we need to think differently. If in the past we look on the problem as sequential problem with nested loops, etc., we need to start thinking about it from the parallel execution point of view and start to look how we can converge the algorithms, and instead of doing the algorithm in the sequential way, what is the equivalence that we have in parallel execution of the system. But as soon as we go over this barrier, so we can leverage all the existing infrastructures, and there's a lot of infrastructure which is built right now for machine learning, but at the end of the day, this is linear algebra. This is what we are solving. Is this point is clear? We'll go to convolution in a minute. This is what is called excellent question, because I have a slide for it. Okay, so just look on, surprising enough, this is convolution. So what we have in a convolution, this ugly expression. And that we have all this nested loop for the convolution. What we are doing in convolution, we'll see. I have a nice chart. Later on, I have here, this is the image, and then I'm taking a window here, and I do some operation with the window on this part, and then I shift it by some stride, and now I have a new window, and this new window I also multiply it by the same filter, and I'm doing it for a lot of windows. Can we represent it as a matrix multiplication? Guess? Yes, otherwise I will not give this class. So how we represent it is this way. So we take this filter, and this filter is 1, 2, 3, 4. And this filter actually we want to multiply by 1, 2, 3, 4, 5, etc. So first of all, we are doing, sorry, we multiply this one by 4 by 4 by this window. Then we shift it by 1. So the first one will be this 4 by this part. And then we shift it. So in the first one, we do 1, 2, 3, 4 multiplied by 1, 2, 3, 4 on the right side. And then we want to do 1, 2, 3, 4 multiplied by 2, 3, 5, 6. And this will be 0.2. And then we'll go and we take it down. So we will do 1, 2, 3, 4 multiplied by 4, 5, 7, 8. And then we'll do 1, 2, 3, 4 multiplied by 5, 6, 8, 9. This is convolution. So we convert it to this matrix. And this matrix, I think that you even study about it, to parallelism matrix. So we put 1, 2, 4, 5. 1, 2, 4, 5, we put it in a row. And then we put the second row 2, 3, 5, 6, 2, 3, 5, 6. And then we put this combination, and then we put this combination. So we pay by space. We multiply it. Again, we just put 1, 2, 3, 4. And if we multiply it by magic, we're getting this matrix as represented here. So this is the entire convolution. Again, you need to think out of the box. You need to look on the structure and to expand. This is classical way that we pay with space in order to get a better execution time. But we convert these nasty loops into matrix multiplication, a simple matrix multiplication here, and we are getting the results. So we can go further, and actually we can also do it with channels, and now we just duplicate it. So this one will be multiplied by this one will be multiplied by that, and we are getting channel 1, channel 2, and we are getting the results. So again, I'm taking something which is C-like or sequential-like. We need to think out of the box and convert it to representation. In this case, this is matrix multiplication, but this representation allows me to do it in parallel with a vast parallelism and with a good performance. And this is part of the reason that in parallel, we know the GPUs that we'll discuss later on know how to execute such structure in a very, very efficient way. And now we actually redesign the data structure in such a way that will fit the problem. And now we can execute vast amount of computations in a very, very efficient way. And this is the secret, how these days we actually can execute very, very complicated algorithms in machine learning in a very, very efficient way. At the end of the class, I will just summarize. I will take you a pipeline of a typical machine learning algorithm, and I show you that we can do the entire pipeline just by matrix operations. Yeah.
Could you calculate the same data in?
Actually, this one is what we saw before. This is just a replication because you want to for each channel you want to do it in parallel. In practice, you may not, if you want to save area, you may want to see if this is read-only, so you can keep it and just use it for two purposes. But at least these are optimization according to the architecture. Yeah.
Do we actually perform the multiplication, or would we use like an FFT or something?
Yes. The simple algorithms are actually do the multiplication. Few of the optimization go to FFT and other optimization. I think that next class I'll start to discuss different optimization techniques. FFT will be one of them. But very good point. So, conclusion. All the operations which are executed in in our deep learning algorithm can be expressed, and I'll show it later on, as operation on matrices. And this is the reason that actually we can do it in a very, very efficient. So any acceleration that can accelerate linear algebra is a very good potential for accelerating machine learning. Saying that, it is not written here, but some of the accelerators can do it in more efficient way than the other. And the main point that, again, I'm not putting here, but I'll discuss it at the end, is that today the main limitation is not the computation. After we pass the barrier of the amount of computation, today part of the problems are communication, power, sometimes in order to save communication. So we are doing pruning, or we try to avoid sparse matrices, and then it starts to be much, much more complicated. But in general, if you ignore all the details, if you just look on the computation part, so there are a lot of means to do matrix multiplication. And just before we finish, something that I will discuss in 2 classes. In the past, people knew that a very, very efficient way to execute algebraic operations is to use something which we used to call systolic arrays. Then people say, yeah, but nobody really need it. Then somebody said, oh yeah, when I was a student, I heard about systolic array. So now we are all using systolic arrays. So there is some trends that start to make sense right now, that we change the focus of the work, and we move from sequential algorithm to this kind of linear algebraic representation. And this is what we'll do in the next few classes. And maybe in the future, people will find out that there is another way to represent it that may be more efficient, but we don't know about it right now. And right now, most of the works, at least in this area, are just converting the algorithm to some kind of efficient representation of matrix, and they do it in linear algebra. So let's talk a little bit about Nvidia. And I will start with something that we just chat in the break with a student. Historically speaking, there are 2 companies that develop hardware for GPUs, or what we call GPGPU, general purpose GPU. By the way, the name GPGPU was invented by AMD, not by Nvidia. And later on, Nvidia tried to change the name, but nobody will to listen to them. The main difference was that Nvidia at that time, when they built this concept, they built the CUDA and the hardware as a hardware software co-design. And we'll see that the hardware reflects the software reflects the hardware, and I can tell you that at that time I worked at Intel, and I was in charge to what they call a technology competitive, and we look careful what Nvidia is doing. And the way that we always predict what Nvidia is going to do, we just look what they are doing in the compiler, and it was clear that these are the features they are putting in the hardware. So it is so tight together that it was clear that if they put something either in the compiler or in the definition of future CUDA, etc., this is something they are actually building, and they have the capability to do it. On the other hand, ATI, that later on was bought by AMD, that later on, because of this deal, almost get bankrupt, but this is a different story. They built an excellent hardware, but as a hardware company, they didn't thought that software is important. So the legend says that they actually gave a few students that came for summer internship and said, okay, build the software to it, and the people will use it. And part of the differences is that Nvidia came with a system solution, and system meaning hardware and software, while ATI or AMD came with hardware solution, and their software lag behind. And the fact that we are today using GPUs mainly is, I think, partly because of the CUDA and the architecture, and not only because the hardware. By the way, later on they also call their processor a CUDA processor, just to even tight the connection to show that they are tightly connected. Okay, so let's talk a little bit about the differences between the CPU and GPU. So we talk about the CPU. Let's talk about the GPU. So in general, it is the same, because if you look inside, you find out that these GPUs are built out of thousands of small, simple cores. And these small, simple cores are nothing else than small, simple cores. So why they are so successful? Because they did something very, very, very smart, and they understood that they're working on throughput computing, which means what they really care is about what is the end result and how fast you can do things, but not about latency. They don't care to give you the result. In most of the cases, very, very fast. They can trade anything. This is one thing. The other thing, which is very, very important to understand, that in the case of Nvidia, they had the luxury that actually the software in this environment is massively parallel. And if we look on the way that CPUs are built in a way that you try to optimize the latency. Because we said that even if you have a small amount of, with a low probability of miss ratio, but you have a long latency, so you suffer a major, major reduction in performance. This is true only if you are looking on the performance of a single thread. But Nvidia said, okay, but we have so many threads that we don't care about the single thread, we care about the system. And we have a lot of threads. So, by the way, for some reason, yeah.
But the entire pipeline architecture is meant to increase throughput, not latency. Latency doesn't change. It changes if you lengthen the pipeline, but the throughput is.
I'll go back to this point in a minute, but you'll see that even in a pipeline, the pipeline meant to increase the frequency. But all the other mechanisms that you are putting inside, like branch prediction and prefetch and all this stuff, are actually meant to reduce the frequency, the latency. You put a very, very fast L1 cache.
It doesn't change, just basically the time that it takes to go through the entire stages of the pipeline. What changes is if you flush the pipeline, then you load all the instructions.
No. What really changed is that if you look on the execution on a CPU, with all these mechanisms, actually most of the time, at least in servers, it's stalled. So you run very, very fast and then you stop to drink water. It's like to drive in the city with a tremendous speed and then stop in every traffic light and wait in the traffic light. So it doesn't help you to drive very fast between the traffic lights, because anyhow the traffic lights stop you.
So this is specific to servers, because in a regular CPU, you don't need that many stalls.
No, in regular server it is less extreme, but it is the same. Most of the time you are, or let's say that even in other application, unless you're talking about very specific applications that they optimize it, so usually the IPC with all the mechanism that they put inside is still around 1.5. But in theory you can achieve a 6 or 7, and you're still around 1. So throughput, but more than that, for just a small example, in CPU architecture, what's happened is that the L1 cache is designed in such a way that it burns a lot of power in order to save few cycles. You could actually achieve the same miss ratio, hit ratio, but to increase the latency to the L1 cache. But it is so important, so you burn a lot of power in order to do it very efficiently. In GPU, on the other hand, if you have memories, first of all, you run in lower frequency, and then you don't care. Because what you care is the amount of about the sorry, the amount of work that you are doing, and not about the latency of single thread. So again, it is nothing that they invent. This principle of operation was known on the late 80s. There was a system in MIT that called Alwife that was built on the very same principles. And then everybody criticized them and said, oh, where you find software with hundreds of threads? And this is the reason that actually they killed the project later on. Now, if you look on Nvidia architecture, a lot of these architectures are implemented in Nvidia cores. The difference is that they don't have hundreds of threads, they have hundreds of millions of threads, which make it very, very reasonable to build it in that way. So what we'll do right now, we'll go over few of the mechanism and we'll show how they change the mechanism in order to save power and to gain performance, assuming that you have a lot of parallelism. And this is the reason that they said that the system is hardware software co-design. You build the hardware because you have different assumptions on the software. You take software that doesn't meet these assumptions and you get nothing. Or you get very bad performance. So, CPU, we said that we have a very powerful ALUs. We have large caches at all levels, and you have very sophisticated control, branch prediction, data forwarding, etc. It costs you a lot of power, and you can actually run it with fast frequency, and you can actually achieve a good single thread performance. So for databases, for example, this is excellent. For many other applications, this is excellent. But they are not taking into account the fact that if you have a lot of parallelism, so you want to build the system differently. So, this is the photo of Core i7. Forget about this access. This is it was published before Intel announced that in this specific die they have graphic cards, and they didn't like the people to suspect, so they just mark it. But in several parts today you have up to 28 cores on the same die. But it looks like that. Look at the proportion between the shared L3 and the core. But if you look inside the core, you find out that about half of the core is L2, and about something like half is the L1 and registers, etc. So you end up that the amount of logic that you really have in the system is something between 20 to 30% at most. All the rest are all kind of mechanisms that don't contribute to the execution itself. So few words about energy efficient. We mentioned it before, so I'll do it very fast. There are many mechanisms in the current architecture in order to reduce and to be more efficient on the memory efficiency. We mentioned that GPUs are more energy efficient, but again, they are energy efficient in compared to the amount of floating point operation that they are doing. They are still consuming something like 300 watts, which is a lot. And these are not mobile devices that you want to put in your pocket, although a trimmed down version of GPUs exists in many of our cellular phones. So if you don't know, if you have Snapdragon of Qualcomm, if this is the chipset that you are using, so you can run GPU application on your cellular phones, and there are some of the applications that you are using it in order to achieve power efficiency.
Usually today in like smartphone, if the smartphone uses any deep learning application, let's say voice recognition or Siri, they compute it in the cloud, or is it happening on the hardware of the smartphone?
Both. It depends. Today, many of the algorithms running on the smartphone, usually they're using special hardware for it. Again, I hope that we'll have time to discuss it. Huawei and many other companies has special devices for machine learning on smartphone devices. But some of the algorithms are running on the cloud, but only if it is very heavy computation. So, for example, face recognition will run on your device if you want to compare it to some database of pictures. Most likely this will run on the cloud. So it depends on the service that you want to get. Okay, so now look on the GPU. So first of all, green here is logic. You can see the differences between how much logic we are using in GPUs and how less or how the control and all the rest are much less. So you may guess that this chart was drawn by Nvidia, because this is not the right proportion. So they are cheating as well. But this is marketing. But in general, this is true that the amount of logic that you are using in GPUs is much, much more than the amount of logic that you're using in the CPU. More than that, the logic here is used for real computation. It's not used for maintenance or prediction, etc. It's used for real computation. And what they are doing about the thermal? Usually they run it in much lower frequency than CPUs in order to compensate. But again, they will not use out of order. They are not using branch prediction. They are not using many other mechanisms. So what they are doing? So actually, they are replacing most of the mechanisms that we know by other mechanisms. First of all, GPUs are mainly supporting mathematical operations. Mainly, they are supporting operation on matrices. So if you look on CUDA on the machine itself, so what you are getting is a operation on n-dimensional matrices that n can be 1, 2, or 3, which is vector 2-dimension or 3-dimension. This is the almost the only data structure which are supported. Right now they are extended a little bit, but the general remain the same. They are breaking down because of limitation that we'll speak later on the system into thread block, and thread block is just subset of the data or subset of the work. And you can have some communication inside the thread blocks, but there is no coherency or communication between thread blocks. So you have a very, very fast mechanism, for example, to synchronize the thread inside the thread block. You have a mechanism to synchronize, but they are much slower at the level of between thread blocks, etc. So a thread by itself is defined as all the operation of the program is executed on a single element of the block. So it can be single, 1 dimension, 2 dimension, 3 dimension. What you define as a thread is always the operation that you are doing on a single operation. So there is no notion of vector, there is no notion of parallel. When you write a system, you write like you have only a single point of operation, and this is mainly in order to make it flexible. We'll see later on that you will say that I want to have small thread block or large thread block or 1 dimension, 2 dimension, everything will use the same thread. So from your point of view, you define it from the point of view of a single point in the system. And threads within the thread block are executed all the time the same instruction. So even though you have many threads, when you define it, you don't know what they will do. All the threads within the thread block, they execute almost the same instruction all the time. The system will collect by itself the thread into structure, which is called wrap. And this wrap can be 16 or 32. 16 is called half a wrap, 32, this is the full wrap. The system will gather automatically by hardware, let's say 32 threads to one structure and will execute it like a SIMT or SIMD. So they achieve the same functionality as AVX or as vector machine, because when you execute it like vector machine. But you don't have the problem that if you decide to change between AVX1 to AVX2 to AVX3 to AVX512, you need to change the software, because your software assumes always that you have a single point, and this single point will be glue into a larger system by the internal runtime. So from your point of view, this is the same exact thread that will run in all the different lengths of the thread. The system will build according to the hardware capabilities. You don't need to care about it. You don't need to care if you don't care about performance, but if you care about performance, you do care about this is a different story, but this is at least the theory around it. And if you will to get 80% of the performance, it works wonderful. There is efficient mechanism to synchronize all the wrap, and there is less efficient to synchronize between the thread blocks. So let's take an example, and this is again to understand how different it is to program between CPU and GPU. So let's take an example that you want to take this vector and you want just to gather all the number which are greater than 0 and put them in another vector with the same order. To do it on the CPU, you need to run this a line that will be order of n. N can be as large as you wish. And this is the way to do it. If you take the same example and you run it in the GPU, so what you do? Since you have order parallelism, so each one of the elements will compare itself to 0 and will write to another vector 0 or 1. 0 meaning I passed the condition, 1 means I fail. So now this can be done in one cycle or one operation. It can be more cycles because it is divided to wraps and etc. At least for one wrap, it is done in one cycle. 0 is false, 1 is true. Now, I just compare myself 0. I'm smaller than 1, I'm greater than 1. Now there is a well-known algorithm, so I didn't write it, that's called Prof sum, that just write what is the sum in this element, what is the sum of all the elements before me. This is a well-known algorithm which is used in many cases. It is log n, and when you run it on this vector, you get it 0, 1, 2, and 3. Because this one sum this one sum all this until this point, so it is 1. Here you have 2 1s, etc. Now that you have this vector, you can go back to parallel. It just says each one we look, and again I'm looking on this is my thread, and this thread actually will say put if you are 0, do nothing. If you are not 0, sorry, I had actually, there's a problem with this 0 and this 0, but it will look if my condition, in this case, if my condition is that I have 1 here, so I'm looking on my location, which is below, and I just put it in this location in the buffer. 1 minute.
How is this with our login?
No, I just skip the algorithm. There is algorithm that I didn't write it to do it in log n steps. The prefix sum. By the way, the algorithm to do it even in more efficient, but you can do it. And this is something that this is one of the algorithms that are well optimized it, so everybody is using it. Most likely, when you study the CUDA itself, I hope that Chaim will give you the algorithm itself. But there are even 2 formats of this algorithm. One format is that it will give here 0, the another format that will give here 1. But these are a basic library that you are getting because everybody is using it. Yeah.
I think there's some dependency between, let's say, the next threads and the threads before.
No. Good point. What you're doing is that actually you says everybody will compare itself to the condition, and then you put synchronize. You must put synchronize, you're absolutely right. This synchronize says no thread can continue until all the thread finish. Now go to the next step. But since this is inside the block, so you can do it in a very efficient way. So this is I try to abstract it out, but yeah, there are more details, but I just give it as an example of a totally different way of thinking about algorithm. Instead of doing something totally sequential, I break it into parallel operation, and one of the common way to do it is to use this prefix sum algorithm. in many algorithms we are using it. Yeah.
Also, I see it's order of one, but that's if you have enough calls, right? Say it's 1 million. The next is the array.
Yeah.
You must have the same number of calls.
Yeah. Yeah. This is you're absolutely right when you say that it is a order of one. It doesn't mean that it is one cycle. It means that you are not depend on the size of the algorithm, at least from the algorithm point of view. In practice, since you have finite number of resources, so you're limited. On the other hand, if you look on the sequential algorithm, there is no way that you can take advantage of parallel system processors, because it can take advantage of only a single processor. Here you can take advantage of all the processors that you have in the system. So if we are talking about, for example, the recent processor that have few thousands of cores, so you can compare few thousand instances in one cycle. So this is the very good way to take advantage of the parallelism. So in that case, actually, it will be here log of n divided by number of a processor that you have, which is much better. So again, the point here is that it is not just a matter of using the algorithm, existing algorithm or the new hardware. You need to think differently. You need to think in a different way, similar to what we showed before, that we take this representation of nested loops of the machine learning and we convert it into linear algebra or different algorithm. But again, the way that we think is we need to think in parallel and not in the sequential. Another thing that I kind of hinted before that we are doing is that I said that we are not doing branch prediction. How come that we are not doing branch prediction? We are running until we reach some condition that we need to stall. Usually it will be a cache miss. And then since there is a hardware that can do it in parallel, so we just switch to the next process and continue from there. So how it can do it in a very efficient way? The way that the system organizes the memory is totally different than the way that we store it in the CPU. In the CPU, we have the registers that whenever we context switch between threads, we need to save the registers and to reload the registers. In the GPU, they actually we'll discuss it in a minute. They have a range of area, which is the shared area. And this shared area can be divided dynamically according to the number of thread blocks that it supported a minute. Which means that the number of registers that you have depends on the number of threads that you decide to run on each core. So it is up to you, and this is the reason that it is relatively difficult to optimize it. It is up to you to decide if to use many threads, that gives you a lot of parallelism, a lot of switches, but each one of them has relatively small number of registers, or to use small number of threads, but with a lot of registers. Of course, you will decide according to efficiency of the compiler to use the registers, etc., according to this parameter, but there is no automatic way to do it, and this is the reason that optimize for a machine for GPUs can take you time. But again, using this mechanism and assuming that it works perfectly gives you a perfect solution without using the branch prediction. It gives you a perfect solution without using prefetch. Because you don't need to prefetch it. The moment that you don't have the data, you have something else to do. And by the time it will bring it. There is a minor problem that right now Nvidia start to suffer out of it. And the minor problem is, and we'll discuss it if we have time at the end or next time, that today we are paying a lot of power for memory transfers. And this architecture for sure trade the cache memory or memories with more data transfer to and from the memory, because if you have many parallel architectures, so you need to read write them all the time. You have small caches, so you have more traffic to the memory. And apparently recently people showed that the major impact of wasting power is memory transfers and not the ALU anymore. All the time we thought that the ALU, and we did all our optimization in order to reduce the number of ALU operations. And recently a measurement shows that the ALU reached to the point that it is more efficient to execute instruction than to access the memory back and forth. So Nvidia also start to change architecture accordingly. Last point that I want to make about the GPUs is the way that they resolve branches. So in branch they didn't stall the system. Sorry, they didn't do the context switch, because as mentioned before, when you have a branch misprediction, you don't have hardware to continue to figure out what is the branch. What they are doing is they are doing a trick which is again, nothing here is really new. It is just to put together the mixture of techniques. So what they're doing, they are using predicates. Predicate is something that is similar to what I showed before, that I check some condition and I raise a flag. Predicates are doing it in hardware. ARM architectures are doing it in their small devices, the 16 bits for decades, and many other architecture. So whenever they have a condition, know that this condition x equal greater than 0, each one of the processors actually do the comparison. So it may happen that some of them it is true and some of them is false, because we are executing in parallel 32 threads. All the 32 execute the same instruction. If for any reason not all the conditions can agree, so first of all it will execute all the conditions which are true. Next cycle it will execute all the conditions which are false. So it will execute from the if to the end to the else. So the first cycle it will execute all the if part. Next cycle it will execute the else part. That can slow you down, and there are tricks to get over it, but in general this is the way that they execute if conditions by using again a well-known technique that's called predicates. Well, there are a few research that try to compare the use of predicate and the use of branch prediction, and apparently there are cases that one mechanism is better, there are cases that the other mechanism is better, but for sure the predicates are much less costly than the branch prediction, and this is the reason that they use to implement it. What's happening if I have a nested loop? If inside if. What? No, the way that they implement it is that they have more than one bit for the predicate. So they allow you until I think 4 nested loops, and then they actually resolve it one by one. So this is the way that they solve. So they allow to have nested ifs. First of all, they check that all of them are closed form, which means that it is not that you jump outside, because they don't know how to handle it. But if it is in a closed form, so actually they allow you, there is some limit, and the compiler can check it, and then they just use it in the 2 bits.
Basically, I shouldn't use ifs in my code. I should try to do it logically.
Yeah, in general, this is a very bad idea to use if in your code. The best is to write code without if, without loops, without anything. I guess that most of us cannot do it. This is also interesting that in the first publication that they came with the CUDA, they write that the justification is that now every thread can run a very long sequence of instructions. Then they realize that because of all the if condition and so on, in practice it is quite short. So they changed the manual. Okay. I'll do it very fast. It is interesting because this is a different way of thinking about the system. In general, I mentioned that in a CPU, all the resources are fixed. They're partitioned between the CPUs and so on. In the GPU, the number of what we call register or shared memory, etc., is dynamic. Is always divided between the number of thread blocks that you define. Which means that if you decide to have less thread, you reduce your parallelism inside the SM, but you increase the amount of memory, local memory, that you have. Something else that, so how they can achieve that register are the same speed as memory? Because in reality, registers and memory are the same technology. It is just a matter that somebody decide to give 32 names to addresses for registers, but you can change it. So for them, actually, it is the same. The memory and registers, they just so if we just look on the structure, so you have a pool of storage, and this pool of storage can be divided to large number, small number, etc. So I see that we are almost out of time, so I just want to, instead of going, maybe next class I'll finish the rest of the material on the GPU, but I want to go to the last slide, and the last slide is okay. What I want you to remember from this class, and again about the GP and so on, I will finish at least the important part in next class. But a typical step it was supposed to be in CNN will include convolution, fully connected, pooling, something non-linear like a ReLU, and batch normalization. Each one of these steps can be done by either purely linear algebra or something which is similar. So we showed about the convolution fully connected. If you look on pooling, so pooling is nothing than to say that the element that want to pull is the thread, and you just need to look on the surround, and actually there is no overlap, so I can do it in parallel. All the pooling I do will use as much resources as I wish. By the way, sometimes I can go from this one and start to activate the next one even without waiting for all the ReLU to finish. for the pooling to finish. Relo is the same, because I can actually activate as soon as I have the value, so I can activate the Relo immediately. I don't need to start any phase. I don't need any synchronization in order to do it. Batch normalization is a little bit more tricky, because sometimes we need to get some averages before we start, so we need to have some preparation. We may, again, I didn't see where, but I'm sure that people are doing it. I assume that we may estimate the number even without accurately calculate it, if we want to save time, or we can do some kind of other approximation to it. But rather than that, we need to have this baseline, which is average of everything, so we can actually do all the rest of the work in parallel, and all the rest, again, this is linear algebra. So we can do all these steps by using different structures of a linear algebra. More than that, most of these cases we can do within the thread block. The only case that we need to be very careful is in the pooling, to make sure that the boundaries are not actually using something which is on different thread blocks. Otherwise, there are tricks to get rid of this problem, but we need to be more careful. Rather than that, in most of the cases, we can actually do it within the thread block, and if we design it properly, so it is tremendously efficient to execute it on a GPU. So next time I will finish the GPU part, but again, I will use this knowledge in order to show you now not just the features, but also how they can be used as part of the machine learning. And then, so next time we'll be focused on the training part and how we use the feature of the GPUs in order to do it in a very efficient way. Questions? Thank you. See you next time.